again. So we are going to continue here with our study of the solar system. We're ready for chapter 7. We finished up chapter 6 last time, where we took a look at those inner terrestrial planets, the inner 4 planets, and quite interesting worlds out there. Now we want to branch out to the outer solar system and take a look at our Jovian planets. Our what are we summary is that we are trapped. Last time we were very comfortable, it said, but we are trapped. We have actually evolved with our planet to the point that we can't survive on any other planet, so without, a spacesuit or something like that. So we are trapped. The Earth is our planet, our environment. So that was sort of our what are we summary. So let's branch out then and take a look at our outer solar system worlds. And they can be studied from Earth. I mean, we can get some information from telescopes, but what's better is anytime we can do flybys or send a probe to it, that gives us a lot more information. So things like Voyager flew past in the 70s and the 80s, Galileo spacecraft in the 90s, Cassini and Huygens, these are named for really early astronomers from the 1600s, but an orbiter and a probe in 2004. Of course, New Horizons is one that made it all the way out to Pluto and gave us some wonderful images. I'll try to show you that, and it's continuing on out into the Kuiper Belt, which extends beyond Pluto's orbit. So lots of good information that we've been able to get. So first off, you're just kind of doing a comparison here. Again, comparative planetology, but the 5 worlds, and we do include Pluto in this, are truly unearthly. They are not like our terrestrial planets. So the outermost, of course, are beyond Mars, but Jupiter, Saturn, Uranus, and Neptune. So 4 out there. These are often called the Jovian planets, or Jupiter-like planets. So Jupiter's kind of like our reference that we work with. However, they have their own separate kind of personalities for sure. And so just kind of in comparison, this is a shadow of one of Jupiter's many moons. I mean, Jupiter has a lot of moons, but Jupiter's more than 11 times the Earth's diameter. It's our largest planet in our solar system. Here's the beautiful Saturn with those striking rings, but we will find that all of the Jovian planets have ring systems. So also the banding that we see, we're noticing some banding. It almost looks like a beach ball that has stripes on it. We also see some banding there on Saturn. This is what we call the belt zone circulation of their clouds, their atmospheres. And it's a little less distinct than what's on Jupiter. Uranus and Neptune out here are about 4 times Earth's diameter. And if you notice, there's strikingly blue color to them, sort of greenish blue and blue colored. And it's due to amounts of methane in their atmospheres. And so that actually, the methane will absorb red wavelengths much better, much more effectively than they do blue. And so the blue gets scattered a lot better. So they tend to have those blue kind of hue to these. But these are just sort of a quick little comparison. And here's Earth, our largest terrestrial planet. But look how small it is in comparison to our giants, the Jovian worlds. So just a quick synopsis, and you might want to make sure you're kind of familiar with those. But Jupiter will be kind of our reference here, and it is the largest of the Jovian worlds. Again, 11 times the diameter of the Earth. Saturn's just a little bit smaller. Actually, the planet of Saturn's a little bit smaller. Uranus and Neptune, even smaller still than Jupiter. Pluto, not included in our little illustration there, is smaller than Earth's moon, so our moon, and it was considered a planet. I don't know if you still in your elementary, junior high, and all then, that time period, learned about Pluto and counted it as a planet, being 9 planets. Well, since 2006, it has actually been reclassified into what we call a dwarf planet. So the Astronomical Union, International Astronomical Union, so IAU, in 2006 voted on this and ended up reclassifying Pluto as a dwarf planet. So it's no longer one of our planets. So some people are very upset about that. Saturn's rings are, striking, very visible. I think I mentioned last time, just even a rudimentary telescope, you can see the rings of Saturn. They're bright and they're beautiful, and they're actually composed of billions of ice particles in them. But I do mention that the other Jovian planets also have rings, okay? They're not easily detectable from Earth, but we've had flybys, we've had other methods that we've been able to actually observe those rings. So our Jovian worlds, our 4 Jovian worlds, these are hydrogen-rich atmospheres just filled with clouds. They are giants, and we can see the stripes on, like I mentioned, Jupiter and Saturn sort of encircling the planet, kind of parallel with the equator of the planet. Traces of these, they're not as easily visible, but we do see them on Uranus and Neptune, but they're not quite as distinct. Most distinct in Jupiter, pretty good in Saturn, but it's a little deeper down in the clouds of Saturn, so it's not as easily seen. But most of our models are showing that, below their atmospheres, Jupiter and Saturn are mostly liquid, so we might want to call them the liquid kind of giants in there. But they're known as the gas giants, but we might want to call them the liquid giants. Let me see if I can write up just a few things about some similarities that we see in our Jovian planets, kind of like what we did for our terrestrial ones. They're very large in comparison, right, to our terrestrial, although there are differences between them. But they're large, they're low density. Call them gas giants. But no, liquid giants might be better. But they're mostly hydrogen and helium. So they're in the solar nebula around the forming sun, and if you remember our little universe cosmology lesson, that in the universe there's mostly hydrogen and helium out there, and so of course these are mainly what these are formed from, a lot of the hydrogen and the helium. And notice that they are far enough from the sun that they can hang on to the hydrogen and the helium. The temperatures are a little bit lower than, say, closer in where our terrestrial planets were located. So they tend to have a lot of the hydrogen and the helium in them. And they're kind of known as gas giants. So they have very thick atmospheres. As opposed to the really thin ones or no atmospheres of the terrestrial planets. They have many satellites, so moons. Okay, and the terrestrial didn't have that much. Of course, Earth has 1, Mars has 2, Venus and Mercury don't have any. So further out, they're so massive, these planets are, that they can kind of gravitationally pull in and capture some of their moons. So they have many satellites. And then the ring systems. They have ring systems. Even though Saturn is the most obvious one, right? The bright and the beautiful ones that we can see easily. they all have ring systems of our Jovian planets. These are some of the similarities of it, of our Jovian planets out there. So the gas giants, kind of. Now Uranus and Neptune, because they're so far out, they do have a lot of ices in them, and so maybe we would want to call them the ice giants. If you recall the condensation sequence, we brought it up and mentioned it in the terrestrial talk, but the farther away from the sun, various compounds are going to be able to condense out the condensation sequence. And so way out there where Uranus and Neptune is, we can get a lot of accumulation of ices now. So they're rich in water and both solid and liquid forms of that. So the ice giants is an appropriate name for those. So near their centers, the Jovian planets have cores of the dense material, composition of rocky and metal material, but very near their centers, and definitely, it's not really what we would think of as a solid kind of surface on these planets that we could walk on or land something on, a probe or something. Not like a solid surface that we would think of like the terrestrial tube. So they're low density. They formed in the outer solar nebula where water vapor could freeze, and so we've got the ice particles out there that I mentioned. And the ice accumulated into little protoplanets, so little baby planets, lower density than the rocky terrestrial planets and asteroids. But once those grew massive enough, they could end up drawing in more of the lower density, the hydrogen and the helium, like directly from the solar nebula, so the forming around our sun that was forming in our solar system. And once they got larger than about 15 Earth masses, they could draw material in by gravitational collapse at that point. So then they could grow like really, really rapidly because of their massive size. So we won't be able to kind of land on the Jovian worlds, but on some of the moons or the satellites that they've been able to capture, yeah, some of those are possibilities in the solar system that we could visit and have put probes and various things on those. So the moons interact gravitationally with it, and this is what affects those planetary ring systems. It's almost as if you didn't have the moons around these planets, they would have no ring system. It's the moons that are supplying either the dusty or rocky material or the icy material that forms their ring systems. And so without the moons, you wouldn't have the ring systems that we see. So some of their moons are geologically active, others are geologically dead, and they'll kind of look at that. Some of them may have had some past activity, but because they're smaller objects, their heat would have dissipated and then they're no longer active. So some of them are really small bodies that it makes you wonder how they could still be geologically active because they're so small, and we'll find that it has to do with their tidal flexing as they orbit around their planet. It actually causes some friction and some heating internally. So we'll see that even with Jupiter here. So Jupiter, named for the Roman king of gods, like the god of all the gods kind of thing. You can see that it's very bright in the sky. We can see its cloud belts in this image here, so that banding kind of look to it. It's our most massive of the Jovian planets. And so it actually has about 71% of all the planetary kind of matter in our solar system. It's, outside of the sun, of course, but it's our massive extra kind of beyond the terrestrial planets. And so we used Earth for our basis for the terrestrial planets. We're going to use Jupiter for our Jovian planets, or our Jupiter-like kind of planets. So that'll be our standard for our comparative kind of analysis. And so we'll be looking at the structure and the formation of the interior of the planets. We'll also look at their atmospheres. We're going to look at the strength of their magnetic fields, kind of what's going on internally, creating those magnetic fields. And of course, we're looking at the ring systems and the satellites, their moons around them, as we kind of go through our comparative planetology study of our wonderful Jovian planet. So, Jupiter's only about 1.3 times denser than water. For comparison, Earth is 5.5 times denser. So it's going to kind of give us a clue about the average composition of what kind of material is making up the planet's interior. So from the shape of the planet, and that'll give us a clue too. This term oblateness, okay, which is the fraction by which the equatorial diameter exceeds the polar diameter. Got something here. The equatorial diameter and the polar diameter, how much it exceeds that, that's sort of the oblateness. So how, you know, spherical are you versus how oblate, okay, maybe squashy look to it. So Jupiter's oblateness, okay, combined with its average density helps them model what's going on in the interior of this. And so they're indicating that because of that observation, that it's mostly liquid hydrogen. Strange. So here on our planet, hydrogen's a gas, right? But liquid hydrogen under those pressures, it would cause it to be liquid metallic hydrogen, a strange kind of substance in there. It's a very good electrical conductor, okay, and so you can get a very strong magnetic field out of this, the rotation of that. So very high pressure, yeah, like I mentioned, the liquid metallic hydrogen, good conductor of it, and most of Jupiter's interior is composed of this strange kind of liquid metallic hydrogen in it. So it does stir it up, getting convection currents in it, and so it gives it a very strong magnetic field, over 10 times stronger than Earth's magnetic field. And so that magnetic field deflects solar wind, okay? It does kind of protect the planet in there. And it's a volume that dominates around the planet. It's called the magnetosphere around the planet. It's able to deflect the solar winds and charged particles. Yeah, and Jupiter emits, well, here's a nice picture of that magnetosphere kind of protecting the planet, and solar winds and particles are deflected from it, okay? Magnetosphere in there. But this so-called kind of rocky core of nickel and iron and silicon, it wouldn't resemble like rocky material that we have here under the pressures that it would be under in Jupiter. But it does have a core in there, rocky core, they're calling that. Now here, something interesting is that the heat flowing out of Jupiter is revealing that it emits about twice as much energy that it's absorbing from the sun. Remember, it's way out there in the solar system, a lot farther away, about 5 AU out there away from the sun. And it's actually not absorbing as much energy from the sun as it is emitting, okay? And so Jupiter's very massive. It has a lot of heat from its formation still, and so it's emitting about twice the energy that it actually takes in from the sun. So it's trying to cool off in there. So that energy does appear to be left over from when the planet first formed, and it's working its way out there. So the heat left over from the formation is actually emitting more energy than it's taking in from the sun. So the atmosphere, they don't have a nice picture, so I'll probably go to the book here. it has that extensive magnetosphere that we kind of talked about. It gives it some auroras around the magnetic poles in there. There's a pattern, okay, the banding, some stripes in there. There's that red, kind of the eye or red spot that Jupiter has, that they're having an understanding that this is just a massive storm that's going on the planet. But this pattern of kind of the stripes, of bands, these are clouds, circulation within the clouds, and it's known as belt zone circulation. And it's related to high pressure and low pressure belts encircling the planet in its atmosphere. Similar to kind of like we have high pressure and low pressure zones on Earth. This is like on steroids kind of thing in Jupiter. Let me switch over real quick for that belt and zone. There's an image, there's a couple pages. Let me see, I think it's page 140 and 141 in your book, okay, where it talks about the belt zone circulation. And so, yeah, these sort of parallel to the equator bands of high pressure and low pressure belts going on. I don't know how well you can see it from there. But the belts are called kind of where sinking, where we would be under high pressure and you would get sinking of the atmospheric circulation in there. Okay, that's sort of the darker orangey color. And then the lighter color would be little regions where there's lower pressure and you get rising of the air. Similar to what happens here on our planet with our weather system, but these bands of it, as you can see along there. So this belt zone kind of circulation, typical of Jovian planets, okay, caused by the rising and sinking of gases, that pressure differences. And it's very pronounced on Jupiter. You do see it on Saturn, but it's not quite as pronounced as it is on Jupiter. Okay, so that's a couple pages in there out of your book that you might want to take a look at those pages. Okay, I don't think they give us a good picture of that. This is also from those two pages as well, where they're just kind of talking about here the different temperatures within the atmosphere, kind of as you're going deeper in the atmosphere. So here's the atmosphere and you're coming down, right, with altitude kind of thing. And what's happening to the temperature here. So there's 100 Kelvin, 200, 300, 400 Kelvin sort of thing as your temperature changes as you come down in the atmosphere, and what the composition would be, what kind of materials would be in there. So on the outermost skirts, the highest altitudes of their atmosphere, you got the clear hydrogen, mainly hydrogen in that atmosphere. You come down a little further, you're getting ammonia hydrosulfide, water in there as well. So I think they're doing a comparison of Jupiter and Saturn on this one figure here in comparison. But yeah, some rather strange compounds that you're getting in the atmosphere there. Ammonium hydrosulfide, yeah. Smelling, that's going to smell bad. But the rings, Jupiter's rings. So, well, of course, we've known for centuries about Saturn's rings, right? They're very bright, very easily seen. But Jupiter's rings weren't discovered until 1979 when Voyager 1 sent us back some photos, right? So they're not as bright as Saturn's icy rings, and they're actually kind of have a sort of a reddish hue or a little bit darker. So they think that they're probably more rocky or dusty material as opposed to the icy rings of Saturn. And so the composition of it varies a little bit. But yeah, the photos show it's very bright when illuminated from behind. So they're concluding that these are very small particles in something that we call forward scattering light, very bright and forward scattering light. So very small materials will scatter light forward. very large ones won't allow it. It'll kind of block the light from going through. So they can come to the conclusion that these particles are very small, maybe even dusty, dust particle size, because it's very bright and forward scattering light. Okay, large particles aren't going to scatter that light forward, and so it would look dark. But these are very bright and forward scattering light. So yeah, that term up there, forward scattering light. So that kind of helps us figure out the sizes of these particles. Very small. Some of them are even, cigarette smoke particle size. So extremely small. The rings orbit in this term here that we have, the Roche limit. Okay, we kind of talked about a Roche lobe when we were talking about our stars. We're gravitationally bound material here. But that's the distance from a planet within which a moon can no longer hold itself together by its own gravity. So these moons can't get too close into their planet, or the gravitational field will be too strong and it would just destroy their moons. But they're saying that these particles are just inside that Roche limit. So the idea is that the moon is kind of supplying these little particles that are then orbiting within that Roche limit. So that raw material, if it gets too close or inside that Roche limit, it can't hold itself together. So those particles are coming off of the moon and they can't coagulate and stay together. So it's like giving the raw material coming from the moons, and it's what's supplying it. Because these aren't going to probably last very long, these little particles. So they continuously have to be replenished in there. So the dusty kind of rings, the little specks get knocked off of the moons, right? Get picked up into the limit in there. It can't hold its gravity together in there, and so you get these little fine particles in there. So you end up having to continuously kind of replenish those as well. And so they can't be new, like we were saying, because that intense radiation around Jupiter is going to just, annihilate it and grind it down to nothing in about 100 years or so. So it has to be, continuously resupplied in there. Okay, so it does have rings, very interesting in there. Okay, the rings of Saturn, Uranus, and Neptune are also short-lived, so they must also be replenished and resupplied by that new material provided from the moons, okay? Eroded off by the nearby moons. So, in addition to supplying the rings with particles, our moons can confine the rings. They're almost shepherding kind of the particles as well. They keep them from spreading out, kind of maintain them in their orbit. So they're shepherding kind of moons, they call them, and keep those particles where they need to be. Now, the family of moons, Jupiter has a lot of moons, but these right here, these are the 4 that are closest in to the planet, okay? These are known as they're the largest ones too, the Galilean moons. These were the moons that Galileo first saw when he turned the telescope towards the heavens and was observing, making observations. These were the moons that Galileo saw. And you can see these moons in a rudimentary telescope, and it's fascinating to see them orbiting Jupiter. So very interesting. But most of the small moons are probably captured asteroids, they believe. So asteroids are leftover rocky debris from the formation of the solar system that kind of got left over. And so probably got too close to the planet, got pulled in, and became the moons of Jupiter in here. So we have Io, the smallest, Europa, Ganymede, and Callisto, right? Ganymede's like our largest one. And so they're probably captured asteroids, they believe, but they're quite interesting. Clearly related to each other and probably formed, as Jupiter formed. after their discoverer, the Galilean moons. The outermost Galilean moons, Ganymede and Callisto, are about the size of Mercury, so almost the size of our smallest planet. 1.5 times the size of Earth's moon, so they're larger. Ganymede is the largest moon in our solar system. So, and you look at their surfaces there, they do look a little cratered, kind of old and kind of battered looking, but they have densities, 1.9 to 1.8 grams per centimeter cube. Rocky or kind of metallic, low density kind of ice, exteriors icy looking. They interact, of course, with Jupiter's magnetic field. That's a very strong field that it goes with, and so it probably does have some mineral-rich liquid water within them, below those icy crusts. Callisto's surface and most of Ganymede's look pretty old. Like I mentioned, the cratering that we see, they're heavily cratered, so that bombardment period, and it doesn't seem like they resurfaced too well. The surface evolution of resurfacing because of internal kind of lava kind of smoothing things out. And so, yeah, you can see some grooves suggesting a little geologic activity in their past, brittle fault systems with these, but they may have some episodes of geological activity going on in them. And then the next one inward would be Europa. That's about a 3 gram per centimeter cubed density. Mostly rock with a thin icy crust. It's pretty clean looking ice as well. Doesn't have a lot of craters. There's a lot of cracks in there, long cracks of the icy crust that kind of resemble here Earth's Arctic Ocean, right, with a lot of cracks in that. So it's kind of an icy crust, but they do believe, because of it's so blatant, that it does have a pretty deep ocean, liquid water ocean beneath it, which is extremely exciting to me. That would have a liquid water ocean that, maybe one day we could go to Europa and dig down and tap into that ocean and explore that, and what would we find? Anytime you have liquid water ocean, there's a possibility for life, so a potential place that there could be some life. And so they do think that this is pretty active geologically, because the water is probably smoothing out the craters that were there. So it has had some good geologic activity. It looks pretty young, the crust does. So here, the one closest into Jupiter is named Io. Io is very volcanically, geologically active. I mean, we can see a lava curtain here coming up in through a fault, some volcanic caldera, which are collapses of tops of volcanoes where the magma has kind of receded, and then you get a collapse, so a caldera. But yeah, you can see very active volcanoes on Io. And so they're thinking, why should it be kind of so active, sort of thing? It's so tiny, it should have cooled off long ago. So why is it geologically active? And so what they're thinking is happening is its orbit is very elliptical. So there are times it's close to Jupiter, and then there's times that it's farther away. And so that will create a tidal friction, a tidal force in and out, creating heat generation. So that tidal heating is what they think is driving that geologic activity on there. So they're very small. It shouldn't have been geologically active, but because it is, that volcanism on Io is driven by the tidal heating. So it flexes kind of that moon, and creates that volcanism that we see on Io. So very interesting. Europa is not nearly as active as Io, but it must have some sort of heat source, presumably tidal heating, to have been able to resurface and surface from all that cratering bombardment in there. Ganymede, no longer active, and lots of craters still on that one. So very interesting little family, the Galilean moons. And of course, they said about 60 other moons. I think they keep adding. There's probably onwards of 70 moons that Jupiter has. So it keeps capturing things. So they keep discovering more. So Jupiter formed very far away from the sun, well, far enough that it's able to get some icy, what we call planetesimals, so leftover icy material as the solar system was forming. It probably grew very rapidly. Once it got 15 Earth masses, okay, more massive than the Earth, it could then grow by gravitational collapse and got very, very massive, directly capturing gas from the solar nebula that was forming around it. So a lot of hydrogen, a lot of helium in it because of this. It was able to capture, it was so massive that it can hang on to the very fast moving hydrogen out there, okay? And was able to get really, really massive, and it resembles the composition of the solar nebula, very sun-like, with all the hydrogen and the helium in it. Okay, the large family of the moons are mostly captured asteroids, as we mentioned, kind of some leftover debris out there. They keep finding some things. They've seen some things strike Jupiter in 1994, some unidentified object in 2009. So, yeah. Again, these moons are what are keeping the ring system going on Jupiter. And any impacts they might get can, put more dust into the rings as well around that. Io, the most densest moon, closest in, and those densities of those moons kind of decrease as you go out away from the planet. And that's similar to the densities that we see as you go farther away from the sun, like our terrestrial ones or the rocky ones. Those are the most dense. You're going out here to your gas giants. These aren't quite as dense as your terrestrial. So that makes good sense that you'd see the same kind of changes in density around your planet with your moons as well. So yeah, so together trying to talk about the differences between the compositions of the Galilean moons as well. So that was Jupiter. That was our kind of reference Jovian planet. And the next one out, a little further out, we have Saturn. The Roman god Saturn, protector of the sowing of seed, is sort of the Roman mythology from this. Of course, the most striking feature are the beautiful rings on Saturn. And so we've looked at the planet's atmosphere, we've looked at the rings and the moons, and here we had Voyager fly by in '79. Cassini went into orbit around Saturn in 2004, explored its rings and its moons, and so we've got some good data about Saturn as well. Saturn has much more faint belt and zone circulation, not as much as Jupiter, right? It's not as pronounced as in Jupiter. So less visible probably because of the very deep kind of atmosphere that it is sort of below a hazy methane layer in the atmosphere. Saturn is less dense than water. And that suggests, like Jupiter, that it is rich in the hydrogen and the helium, and the oblateness of it can tell us something about the interior. And Saturn's the most oblate of the planets, and so that does show us that it's mostly liquid, metallic hydrogen, and maybe a core of those heavier elements at the core, but it's certainly no surface that you could land on for sure. Okay. So its internal pressure is lower on Saturn than Jupiter. It definitely has less liquid metallic hydrogen, which that's going to affect the magnetic field. And so Saturn has 20 times weaker a magnetic field around it, that magnetosphere, than Jupiter does, okay, because it doesn't have quite as much liquid metallic hydrogen. And like Jupiter, it also radiates more energy than it receives from the sun. So it's still, radiating from its heat of formation, we kind of call that, but it's also doing similar to what Jupiter does, radiating more energy than it gets from the sun's. So the Saturn's rings, there's actually a page in there that we may flip to, I don't know, we might if they don't show a picture in here, about Saturn's rings, and it would be pages 146 and 147 in your book. But something important to note about Saturn's rings, that these are icy particles as opposed to that rocky kind of material of Jupiter. These are icy. They're made up of billions of ice particles that are each in its own little orbit around the planet. And the ring particles you observe now, can't be as old as Saturn, and these have to be replenished. And so little impacts on Saturn's moons are what kind of replenishing the rings, okay? So same thing holds true for the other Jovian planets. The moons are the reason that we see the rings around it. They are the ones that are replenishing that. So without the moons, there would be no rings. So yeah, and so the gravitational effect of the moons can confine some of the rings. Actually have some little gaps that we talk about. A Cassini division, they call one of them, that I don't think is going to be in a picture for us. I may turn to that real quick. But the moon Mimas, one of Saturn's moon, Mimas, actually keeps this Cassini division. Right in here you see it's a gap. The Cassini division is a gap, and it's controlled by Mimas, one of Saturn's moons, okay, that it has. So it's what's kind of the gravitational interaction of Mimas keeps those particles to the point that it keeps a nice gap in there, and that one's called the Cassini division. You probably can't see that, but it's on the 2 pages in your book that you should take a closer look at. I would say, I would recommend that. But again, sort of a shepherding type of moon that keeps those rings, the edges of the rings nice and sharp in there. So the ring particles are confined to the thin plane. So it's in the plane of Saturn, confined to that, and certainly within the Roche limit as well. We mentioned that with Jupiter, are within the Roche limit as well. Okay, that minimum kind of distance that the moon has to stay a little ways away from that, but all these little particles will form the rings within the limit of the Roche. And they are going on orbiting around Saturn within the plane of Saturn, and there's all these icy particles in there. So they're controlled by their planet's moons. Saturn has 60 known moons. They're containing mixtures of ice and rocky material out there. I mean, you're small, probably captured objects. The largest of Saturn's moon is Titan, which is a little bit bigger than Mercury, tiny planet Mercury. And its density suggests that it's probably a rocky core with some a mantle of some ices, so some strange little things going on there with Titan. There's this interesting kind of picture of Titan that they sent a probe to look at. But this is kind of described as an organic goo, kind of looks orangey colored in there, but that these would be some carbon kind of rich molecules creating sort of a smog out there. But they've had a chance to kind of send a probe to Titan. Okay. Looking at kind of the ices, water and methane. Strange to think of methane as an ice, but the temperatures are really cold. Here on Earth, methane, is a gas. But minus 180 degrees Celsius, you're going to get some ices, even methane ices. So Cassini and Huygens. Cassini is the spacecraft, and then Huygens was the probe that they went and got some good information about Titan. And so the methane could actually fall like rain. So strange. And washes kind of the dark goo, the organic material, off of the higher terrain and kind of downwards to the lowlands. So they are kind of seeing some drainage channels, these grooves that they're finding on Titan. Quite interesting as well. So methane downpours kind of thing, strange stuff. Okay, and then another one they have, Enceladus. This one's Enceladus, almost looks like tiger stripes on it. Very small, icy, no atmospheres, heavily cratered. Yeah, we see a lot of craters on there, and so they're pretty ancient surfaces. There are some places where on Enceladus there may have been some recent geologic activity, right? Because it's got a few bit craters in comparison to some of the other ones. So again, tidal heating, as it got closer and it got farther away from the planet, it could activate that internal heating. So warmed by tidal heating, that may have smoothed out some of those craters from that heavy bombardment period. But that's Enceladus. And Enceladus kind of maintains the E ring that is extending beyond the visible rings there. And so the shepherding moons that are kind of keeping those rings in place. Very interesting family of moons for Saturn. So Saturn, beautiful rings, very brilliant. They all have rings, but Saturns are really easy to see. Uranus, so our next planet out from Saturn. Okay, Uranus, and so these guys, these two outer ones, let's see, Uranus, primordial god of the sky. It's like the most ancient of the Roman gods. Uranus, they kind of stick with that mythology theme for the naming of these. So our gas giants, right, we have, well, these are a little different. You might want to call these the ice giants, actually. And they're not as similar to our, very large ones there. They have some similarities, but they're actually quite different. They're not as large, for sure. That's the first striking thing. But Uranus was discovered by William Herschel. We heard about William Herschel and his sister when we were talking about how to kind of come to the realization that we actually lived within a galaxy. They did some work on that. But William Herschel was the one that discovered Uranus and kind of trying to figure out a name for it, and he was going to name it after the English King George III. And that didn't go over too well, so they kind of went back to the mythology thing and stuck with that for Uranus there. Uranus is only about the third the diameter of Jupiter and not near as massive, 20th as massive, and it's 4 times farther from the sun, so it's really way out there. Its atmosphere is over 100 degrees Celsius colder than Jupiter's, so the farther out you go away from the sun, yeah, your temperatures are going to be lower. But Uranus never really was able to grow massive enough to capture large amounts of the gas from the nebula like Jupiter and Saturn did, so it didn't get as massive. So it has much less hydrogen and helium. And of course internal pressure is much lower, to the point that it probably doesn't contain the liquid metallic hydrogen like Jupiter and Saturn does. Its density and its oblateness kind of tells us that it has a small core of heavier elements, and a deep mantle of partly solid water. And even though it's kind of termed ice, well, it really would not be similar to ice here on our planet, given those temperatures and pressures inside of Uranus, but they're kind of calling it icy in there. So the mantle has a little rocky material, strange stuff like ammonia and methane in it, so it does give it a little bit of a nice electrical conducting mantle in there, and hydrogen and helium in the atmosphere, okay, as well, similar. Now, strangely, Uranus rotates on its side. Where'd my little demo go here? So most of the planets have a bit of a tilt. You know, the Earth has about a 23.5-degree tilt, that kind of thing. And orbits like Uranus is like knocked over on its side to where that its equator is about 98 degrees, okay, to its axis of rotation in there. So it got disturbed somehow quite severely along the way in here, and it kind of gives it very extreme winter-summer contrast. You know, we do get our seasonal changes because of the tilt, as we mentioned earlier on, but this one's got some extreme winter-summer contrasts in there. But it got knocked over on its side, and if you remember, in the last one, we alluded to the fact that Uranus and Neptune probably formed closer in to where our terrestrial planets were, and then they migrated out, farther out in the solar system. So maybe along the way it got knocked around quite a bit and got it tilted over on its side like that. So yeah, that's some of the speculation on what happened to Uranus there. So it's got a little bit of a, you know, a magnetic field kind of thing, rotating on its side. Let's see, I think we already had that. And that odd rotation, like it mentioned there, was probably struck by some planetesimals late in its formation, that kind of late heavy bombardment period. It was migrating kind of out and got knocked around a bit. So again, strikingly blue. And that is from those traces of methane, okay? Methane will absorb in the atmosphere. It will absorb red light, red photon lights, wavelength lights, a lot more easily than it does the blue, and it scatters the blue very effectively as well. So it's kind of a blue-green or a teal kind of color to Uranus, and it's due to that methane, the trace of methane in its atmosphere. Green, blue, kind of teal color. So the belt zone circulation, they were kind of not able to see it very well, but here's a computer enhancement that does show it, okay? And since decades that they've come back with Voyager 2 flying past Uranus, the season has kind of changed to, you know, spring and autumn kind of thing, to where that may have reactivated its weather pattern, its circulation. So they do see the belt zone circulation not near as pronounced as on Jupiter and even on Saturn, but it does. It has belt zone activity going on. It's showing that Uranus is radiating about the same amount of energy as it is receiving from the sun, so that's fairly, you know, intake and output is pretty balanced. And of course, it's you know, much less heat flowing out of its interior than Jupiter or Saturn would. But that may account for its limited atmospheric activity, why that first flyby they didn't see the belt zone circulation. But Yeah, so it does have the belt zone circulation, though. All of your Jovian outer planets do. So until recently, we only saw about 5 moons of Uranus, but again, Voyager 2 discovered another 10 in there, and so again, captured kind of objects from these 5 major moons. They're smaller than Earth's moons. Very old, kind of dark and cratered surfaces, so haven't smoothed out their surfaces since the bombardment period. Very strange, some liquid water lava maybe erupts and smooths out some of those, so interesting on some of the moons of Uranus. Miranda is the innermost moon, and it's about 14% the diameter of Earth's moon. It does have some little ovoids or grooves in it. You can also see a lot of cratering in this, but they may have been caused by internal heat kind of driving a little bit of convection in that icy mantle there, but it's still pretty old kind of surface, and they don't think it's really active any longer, geologically active on that moon there. So Uranian moon. And the rings, the Uranian rings, and so they're very faint, a little dust in them. They are confined by their moons, of course, the shepherd satellites they call that, and must be continuously resupplied, right? They're not easily visible from Earth. It was not until we saw through an occultation. So what an occultation is the planet Uranus went in front of a star, okay? And the rings of Uranus actually blocked a little bit of the light of the star. So this is known as an occultation. And so they were discovered during this occultation of the rings and the planet too in front of a star. And it helped us to envision these. So the passage of the planet in front of a star, an occultation, is how they discovered the rings of Uranus. So that was an interesting discovery as well. So flybys again, spacecraft Voyager 2, looking like their compositions are sort of watery ice mixed with methane, so some strange kind of combinations in there. Very faint kind of rings, even farther out than previously known, so we keep learning new things about it. New satellite, MOB, okay, which may be the source of the particles for those very faint rings out there. And notice the names of these moons, Portia, Rosalind, MOB. These are names from the Shakespearean, the heroines in Shakespeare's novels and plays. So the International Astronomical Union had declared that all the moons of Uranus should be named after characters in Shakespeare's plays. So that's kind of the theme they've got going on for the Uranian moons. Okay, that's Uranus, and so go a little further out at Neptune, right? Also vividly blue, so that is due to the methane, and it probably has about 1.5 times the amount of methane than Uranus does, so it's got an even more brilliant kind of blue to it. But Neptune was actually theoretically calculated that there should be a planet there because of the gravitational field of what was going on with Uranus. They were thinking those irregularities in the motion of Uranus, there's got to be a planet there. Why is it behaving this way? There's got to be a planet out there. So it was, French and British astronomers independently kind of calculated the position where Neptune should be. And well, they're saying the British astronomers were too slow to respond, and so Neptune was discovered in 1846, and the French astronomers got the credit for that. So we don't see a lot of cloud features on Neptune, but they used I think, is it Roman or is it Greek? Let me just make sure on Neptune. Oh, I don't know, Roman or Greek, one of those, god of the sea. Yeah, it's kind of blue looking, god of the sea there. So I can't keep the Greek and the Roman stories straight. But yeah, so not a lot of clouds going on there. But Voyager 2, of course, in '89 flew past and revealed some of Neptune's secrets in there. It's about the same size as Uranus. Its interior is similar, so the very small cores that these have, slushy kind of mantle of ices, water in there. Below, again, a hydrogen-rich atmosphere that they have. Dramatically blue, active cloud formations in it, so they've been able to catch a little bit about their atmosphere. 1.5 more times of methane in the atmosphere, creating the blue, because, and they're finally telling you why, but methane absorbs red photons better than blue, and it actually scatters blue photons better than red. So the blue hue that we see from that is due to the methane in the atmosphere. Okay, atmospheric circulation is more dramatic on Neptune than on Uranus. And so flybys again, Voyager, it actually had a great dark spot on it, roughly the size of Earth. It's related to atmospheric circulation, similar to the great red spot on Jupiter. You know, these raging kind of storm sort of things. But smaller spots were visible in Neptune's atmosphere. So it does have circulation similar like our hurricanes here on Earth. But it's gone. The Hubble Space Telescope said it's kind of gone, and new cloud formations have come, and so there's changeable, very changeable weather on Neptune. Let's see, so it's way out there, about 30 AU from the sun. That atmospheric activity is heat flowing out from the interior, so it is losing energy from the interior. But also, I mean, it's way out there, but it still does get some sunlight that contributes perhaps to its weather as well in there. And it seems like Neptune might be a little more atmospheric active than Uranus is, and probably because it has more heat flowing out of its interior. Highly inclined magnetic field, so that must be linked to the interior magnetosphere conductivity in there. Again, ammonia dissolved in liquid water makes good electrical conductor in there. Coupled with the rotation of the planet gives it that dynamo and generates a pretty decent magnetic field around it. So 2 moons were discovered from Earth, actually, before even Voyager flew by. But since that discovery with Voyager, we've got 6 more moons in there. And the 2 largest ones have some pretty strange orbits. Triton is like that large one. It's nearly 80% the size of Earth's moon, and it orbits backwards from what you would normally think. It's clockwise as seen from the north. So it orbits what we call retrograde. We've kind of used that term retrograde, which is opposite of what is normal. And there is a normal kind of theme in the solar system that things rotate counterclockwise and they orbit counterclockwise. That's a pretty general theme that we do see throughout the solar system. So for this to have kind of a retrograde or opposite type of rotation or orbit around Neptune is odd. It's quite peculiar. But that odd orbit suggests that the system was disturbed long ago with an interaction of some other body, maybe a massive planetesimal. And again, recalling that I mentioned that Uranus and Neptune formed closer in the solar system and then migrated outward. So perhaps during their migration outward to the outskirts of the solar system, they were disturbed along the way, and it could have knocked the moon a little awry, creating that odd rotation. Okay, so Triton, they've taken a look at Triton, nitrogen and methane in its atmosphere. Triton's ice is a significant part of it is ice. It may have had some active past to it. It has a few craters, and it looks like the icy crust probably broke in places there. Some large basins that probably got flooded from the liquid interior and smoothed out a little bit. So probably some activity on that one as well. I mean, that's way out there too. There. Neptune's rings, very faint, very hard to detect from Earth, but again, that same kind of method, occultation, we were able to get a look at Neptune's ring system as well. And again, they are apparently resupplied by impacts of the moon, scattering that debris, and it falls into stable places in orbit. So we're seeing the rings here around the disk of Neptune as well. And these again, very bright in forward scattering light, so very small particles as well, indicating significant amounts of dust and very short-lived particles, okay? Short lifetimes that have to continuously be supplied. So bright in forward scattering light. We know they're very, very small because of that. Kind of a fitting title here. So Pluto. Pluto's even further out beyond Neptune's orbit. But Pluto, planet no more. Kind of sad, and it really has upset a lot of people. That way out there in the edge of the solar system, small icy worlds. Pluto was discovered in 1930 of these icy worlds out there. But we've seen more icy worlds out there now. I mentioned the New Horizons that is actually imaged Pluto. I'll try to show you that here in a second. But it's found more icy bodies out there, some that are even larger than Pluto. So, yeah, in your school, you probably learned that there were 9 planets. Well, sorry. In 2006, the IAU voted to remove Pluto as one of the planets and reclassified it as a dwarf planet. Okay, Pluto is a small icy world. It isn't Jovian and it isn't terrestrial either, so it's kind of its own thing out there. Very highly inclined in its orbit, very elliptical in its orbit as well around the sun. Doing some comparative planetology, when we look at its neighbors in there, it's only 65% of the diameter of Earth's moons, pretty small. Shows little detail. Yeah, this is sort of the orbit that it's done, and it's got several flyby period of 1979 in there for that, but it's very far from the sun, and it's very cold out there that things that we think of as gases can freeze at those temperatures. So strange kind of composition. Nitrogen, we think of nitrogen gas, right? Nitrogen ices now. This far out, carbon monoxide ice, okay? Methane ice. So strange ices out there that we think of as gases. Here, Pluto has 3 moons. It actually has 5 moons, but they're saying it has 3. Actually has 5 moons. Nix and Hydra are quite small. Charon or Charon, which way you like to pronounce that. Charon is like the god of the underworld, right, I think, or something like that. No, Pluto's the god of the underworld. Charon was the ferry boat man that took your money and would kind of row you down the river Styx towards the underworld. That's who Charon was. all the mythology stories that go along with it. But Charon is actually kind of large in comparison to Pluto. It's about half Pluto's diameter. But it orbits Pluto in about 6.5 days or 6.4 days, highly kind of inclined to the ecliptic in there. But they're tidally locked, you know, so they're facing each other. But can kind of tell us a little bit of something about them. If we know the diameters and the masses of them, we can kind of calculate their density so we can get a feel for what their composition is. And so Pluto and Charon must be 35% ice and about 65% rock material. And so that kind of gives us a clue on their composition. Hubble Space Telescope didn't really reveal a whole lot about the icy moons. Maybe some craters on there, signs of tidal heating that might happen caused by interaction with Charon. But that gave us some fantastic details was the New Horizons spacecraft, and it said will fly by in 2015. Well, 2015 has passed. They're old PowerPoints. It did fly by in 2015 and radioed back some very interesting. Let me go look at that real quick. Images, if I can get that to pull up. And so there are images, and they did a montage of the pictures to create, see if I can get it to show. It's a little tiny Pluto right there, and so as the New Horizons spacecraft got closer and closer, they were taking images the whole time. And you'll see a little tiny dot that is orbiting it. That's Charon, oh, if I can get it, moon. Pluto's moon that orbits around. So they're little tiny. May not show up too well, but every now and then you see a little speck, and that's Charon orbiting. So they're getting closer and closer as the spacecraft gets closer, and it begins to show some amazing kind of details of Pluto. I don't know if anybody's seen the big heart image that we see on Pluto. There we go. And they're getting closer and closer. I'm going to kind of take a look at the surface. You do see cratering on the surface and some smoothed out kind of regions as well in there. And we're going to take you, closer and closer, amazingly close. I mean, a spacecraft that went to Pluto, flew by Pluto, and got these images. So, yeah. Come on now, let's get closer and closer. So, a simulation of a landing. We didn't land on it, but pieced together, right? It took it 9 years to get out there, 3 billion miles to get out there. And this was created over more than 100 images, and it completes that first kind of mission of all of our classical planets, right? And it's going on. It's continued on, and now it's taking a look out there in the Kuiper Belt that they mentioned in there. So let's see, getting back out of that. Yes, so some wonderful details that we're able to see from the New Horizons spacecraft. It was extremely exciting to be able to go that far out in the solar system. And it's continued on out into what we call the Kuiper Belt. Now, to understand why we don't call it a planet anymore, and we reclassified it as a dwarf planet, we need to kind of have an idea of what our planets will do and why it's not considered a planet. So the Kuiper Belt is out there beyond Neptune's orbit, and it's lots and lots of icy bodies, these planetesimals, known as just leftover icy bodies from when the solar system was forming out there. Yeah. From outside the solar system. That's the Kuiper Belt that they talk about. They found another one called Eris that's 5% larger in diameter than even Pluto is. And since then, they found a few more, Sedna, Orcus, and they're about half the size of Pluto in there. So they found some other objects similar to Pluto out there. Some of those have moons of their own as well. But Pluto is not Jovian, it's not terrestrial. It's got its own kind of class, its own family of an icy world of many of these other ones that we've discovered beyond Neptune in the Kuiper Belt. So they probably formed about the same time as our 8 classical planets formed, but they're leftover debris, okay, these icy bodies, and they did not grow massive enough to clear out their orbital zones, these remnant kind of planetesimals, okay, and they remain embedded as a swarm out there in the Kuiper Belt. So to be a planet, you must be massive enough to bring your shape into a sphere, which Pluto does. Okay, you must orbit the sun. That must be the center of your orbit. Pluto does that. But that third critical factor here, that they have not cleared their orbital zone of all other debris out there. And so that key kind of factor there didn't clear its zone, gave it that new kind of category of a dwarf planet. So that was the main thing. Yeah, criteria for a planet: large enough to dominate gravitationally and clear its orbital region of most or all other objects, and Pluto doesn't do that. Okay, and the Kuiper Belt do not meet this standard, and so that got voted on in 2006, and so we have Pluto being reclassified as a dwarf planet, okay? A new type of objects that are defined by the IAU. Dwarf planet, that's what happened to Pluto, and I'm telling you, that angered a lot of people. But it was voted on. International Astronomical Union, many members in that, and voted that. So over a dozen Kuiper Belt objects are known that they're getting caught up with Pluto in a resonance. They call this 3-2 resonance with Neptune, meaning they orbit the sun twice, whereas Neptune orbits it 3 times. So this 3-2 resonance that they talk about, and they're calling those Plutinos. And of course, these formed way out in the outer solar system. So how they end up getting caught in resonances with Neptune? Again, earlier on, this suggestion that Neptune and Uranus were forming closer in, okay, maybe even near the terrestrial planets, and then migrated out. So during their migration out, they may have swept up these icy bodies, and they kind of got linked in that resonance. So it appears that we can kind of predict that Uranus and Neptune actually did migrate outward, and this idea of the Plutinos being in resonance with Neptune kind of helps support that model in there. So. And of course, that would have dramatically upset their motion of some of these Kuiper Belt objects, thrown them inward, interacting with the Jovian planets. Many of those icy bodies could be what got captured, would have gotten captured by the Jovian planets, and so that's what some of the moons may have ended up being. But those small kind of frozen worlds on the fringes of the solar system may hold the clues of the formation of the planets 4.6 billion years ago, sort of the age of our solar system objects, a common age to our planets in there. They all kind of formed at about that same time as the sun was forming. And if you Remember we mentioned that the sun's about middle-aged, just about a 5 billion-year-old star, and it's got maybe another 5 billion to go. So around that same time, the sun's forming, the solar system forming. There's a lot of commonality in the ages of our planets and our moons and that sort of thing, asteroids and comets, some leftover debris in the formation of the solar system, and which is what we're going to, in chapter 8, really talk about the origin of the solar system. But this just gives us an overview where we're looking at the Jovian planets. We looked at the terrestrial planets. We included little Pluto out there. You know, it's got one very large kind of moon. It has a Charon that was orbiting around it. So a new class, the dwarf planets. They're no longer one of our classical planets. Pluto. But that gives us sort of an overview of the entire kind of solar system, taking a look at the planets and a few of these extra little bodies, asteroids, the Kuiper Belt objects, the icy bodies, which may be the origination of where a lot of our comets come from. Comets are icy bodies, sort of space debris. Which leads us then to chapter 8, where we are going to look at the origin of the solar system as a whole. So make sure you got your study guide and that you can answer all of the questions on the bullet by bullet on your study guide. And I'm going to see you next time for the origin of the solar system on chapter 8. So I'll see you then. Bye-bye.